Okay, then I will start today's class. Uh, Welcome everyone. My name is Rahul Jadhav, and this is the interactive session 4 for the polymer reaction engineering. So we will be going through some sample problems so that you can solve your assignment number 4. Starting from the first question, for the recycled reactor, select the incorrect option. Which one is the incorrect option among solid? So first we'll take a look at the schematic right here, which is telling us what is the recycled reactor. So what happens in a recycled reactor is that you have a feed flow rate coming inside. You can see it from the left hand side. This entering the reactor, and then the reaction occurs. And then, as the outlet feed flow rate is flowing out, we can see that it diverges into two parts. One is the product stream, which comes out on this side, and the other side is going back to the reactor itself. So that this side is the product side. You can see that. And then on the other side, we can see that some of it is purged, and the rest of it is being sent inside the recycle. So this recycle uh, stream is again sent back to the reactor. This is usually done to increase the conversion and the yield, product yield. So since there is some any kind of unreacted reactants left over, that can be recycled back inside the reactor and the reaction can. So here has been given. First one is the product stream is split and returned to the entrance of the reactor. So this is correct. This actually adheres to the definition of the recycled reactor. So this is the correct option. But we have been asked to choose the incorrect option. So since this is the correct one, this is not the answer. Next is the conversion of the reactant is decreased due to returning of the product stream to the entrance. Now, again, this defeats the entire purpose of the recycle reactor because this is the incorrect option. Because the whole reason why the product stream is sent back to the recycle is because any of the unreacted reactants are there that can react and increase the conversion of the reactant. So this is the incorrect option here. So this will be the correct one. We'll take a look at the rest of the two also. The recycled ratio can be defined as the ratio of the volume entering at the entrance of the reactor to the volume leaving the reactor system. Again, this is right. The recycled ratio can be defined as the ratio of the volume entering the reactor and the ratio to the volume leaving the reactor. So that will give us the how much percentage is being recycled back. So that is correct. Next, if the recycle ratio R is infinite, then the recycled reactor approaches to the next flow reactor, and the performance equation of the recycling reactor will become the same as the performance equation from the MFR. Now, uh, what is happening here is that we have the recycle ratio R is becoming infinite. And if the recycle ratio is becoming infinite, it means that no product is going outside. All of it is being again circulated inside the reactor. All 100% product is being circulated back inside the reactor, which means that the reactants are just going to spin around in this loop. So they are effectively getting well mixed. And that is nothing but your mixed flow reactor. So yes, if the recycle ratio is infinite, then the recycled reactor will approach to the mixed flow reactor, and the performance equation of the recycling reactor will become the same as that of the MFR. So the correct answer for this question is option number B. That is the conversion of reactant is decreased due to the returning of the product stream to the end. Moving on to the next question. For irreversible parallel reactions, A giving R, which is the desired reaction with rate constant K1, and A giving S, undesired reaction with rate constant K2, the rate of disappearance of reactant A can be written as. So we have a parallel reaction going on. In parallel reaction, the reactant is converting to two products, either desired and undesired, at the same time. So these two reactions are competing with each other. So they are also called competing reactions. And these reactions are irreversible in this case. And you can see the schematic that A is converting to R with the rate constant of K1 and A is converting to S with the rate constant of K2. So it is asking us that the rate of disappearance of reactant A can be written as. So from the you can start by writing the dCA by dt expression itself. So the rate of disappearance of A can be written as the rate of formation of R and S. So the rate of formation of R will be the rate constant multiplied by either the decomposing concentration of A for R and same thing goes for K2. So amongst these, you can see that the first expression K1 minus K2. When there is a negative rate constant right here, it is used for the reversible reactions. When there is a reaction going back, for example, if R is converting back to A, we will have another sign right here, which will be having some rate K2 or K3, something like that. And in that case, you can write it as negative K multiplied by C. So the first one is incorrect because our reaction is reversible, irreversible. Sorry. Then in the next one we have K1 multiplied by C. This is not true. Why? Because this is only taking into account A forming R because it is only having the it is only having the value of K1 inside. So that is incorrect. Next is zero point 0.5 multiplied by K1 by K2, K1 plus K2 multiplied by C. Again, in this, you can see that role of zero point 0.5 has no uh, reason to be here in this expression because it's not going to get equally divided. It depends on the selectivity and it depends how the which reaction is more favored. For example, if the order of reaction of R, that is K1 Ca power something, is higher than that of S, reaction K1 will be more favored and the reactant will be more favored to go in that direction. So you cannot write this also as the correct answer. The correct answer is K1 plus K2 multiplied by C. Because this is a straightforward expression which is showing that whenever the reactant is undergoing a parallel reaction, it will decompose equally. It will decompose on both ends with K1 and K2. So just add both of them, K1Ca and K2C. K1Ca will form R and K2Ca will form S. So that will be the correct answer for this question. Moving on to the next one. If the recycle ratio R is 0, then the recycle reactor approach to plug flow reactor and the performance equation of recycling reactor will become the same as the performance equation for the PFI. Again, in the first problem, we saw that there was a statement where it was saying that recycle ratio is becoming infinity. Now, if the recycle ratio is infinity, which means that all the product stream is being circulated back inside the reactor. But in our case, right now, it's saying the recycle ratio R is 0. This means that there is no stream going back inside the reactor. All of it is going out as a product. And this phenomena is often seen in plug flow reactors. Plug flow reactors are described as long cylindrical reactors like this, where the material is flowing in plugs. Plug flow. It's a special type of flow. Plug flow. It is going in like this, and then it passes through the entire length of the reactor, and then it comes out on the other. So here there is no back mixing involved if we are taking the ideal plug flow. Since all the elements inside the plug are going as it is, there is no actual mixing involved here. And we can see that that corresponds to the reactor which is shown here because the recycle ratio is 0. So the recycled reactor approach to plug flow rate. So that's why this is true. This statement is true. It's a pretty straightforward question. Moving on to the next one. Choose the correct option for multiple reaction system from the following statements. Statement 1 is, for multiple reaction systems, there is a need for minimization of the undesired product and size of the reactor to maximize the desired. Again, whenever there are multiple reactions taking place, that is, again, looking at the second example, you can see right here, where A is decomposing in R and S. So you can see that there is a need for us to minimize the undesired product. That is true, correct? And the size of the reactor to maximize the desired one. If the size of the reactor is smaller, and if the minimization of the undesired product is dependent upon only the kinetics of the reaction, but still, if the desired reaction is not favored and you're using a smaller reactor, then we are basically reducing the possibility for the undesired product to be formed because the reactor itself is small, and since we are not providing any more residence time to the undesired product to form, we are minimizing the undesired product and the size of the reactor to maximize the desired. So that will be true. Statement 1 is true. Next, we have statement 2. For multiple reaction systems, there is a requirement of more than one rate expression to describe its kinetics. So we have multiple reaction systems acting together. There is a requirement for more than one rate expression to describe its kinetics. Again, let's go back to this example. You can see right here that we have A giving R and S, then we have K1 and K2 here. This can be depicted with a separate kinetics expression for A giving R and separate kinetic expression for A giving S. And in other cases also, if there are more than 2 to 3 products forming, then the reaction scheme becomes more complex and you definitely need more than one rate expression to describe the kinetics. So yes, statement 1 is true and statement 2 is true. Option A is the correct answer for this question. Uh, I hope I'm audible and
Yes, yes,
you are.
very good. Actually, we are hearing good explanation. Please go
Yeah,
ahead.
okay. Yeah. Okay, then let's move on to the next question. For different types of multiple reaction systems, select the correct statements. So we have been given 4 statements here, and here we have been given again the multiple reaction system scheme. We have There are 2 schemes right here where there are again multiple reactions happening. On the left hand side, I have a scheme where a parallel reaction is taking place, where A is forming B and C with kinetic rate constants K1 and K2. And on the right hand side, I have a scheme where A is forming B with the rate constant K1 and then B is forming C with the rate constant K2. Again, there are multiple reactions here also and on the left hand side also. So let's see the statements and which is true and which is not true. Let's take a look at it. In a parallel reaction system, the reactants are consumed by the different reaction pathways to form different products. Okay. So the first one, it is asking us that in a parallel reaction system, that is the left-hand side reaction, the reactants are getting consumed by different reaction. Yes, A is forming B and A is forming C. The rate constants are different for both of them, so definitely the pathway for the reaction is also different. Either the order of A forming B is higher, or maybe A forming C is higher than the other one. So the reaction pathways are different in parallel reactions. That is true. Next, we have in series reaction systems, the reactant is consumed to produce an intermediate product which reacts further to produce the final. So again, on the right hand side, we can see that B lies right here in the middle of A and C. C is the final product which is desired, and A first gives B with a rate constant of K1, and then B forms C with a rate constant of K2. So that's why in series reaction systems, the reactant is consumed to produce an intermediate product which reacts further to produce the final product. So this statement is also true. In a complex reaction system, both parallel and series reactions are involved. Now this statement is quite questionable. Why? In this, it is saying that both parallel and series reactions can happen in complex reaction system. And this statement is true because in nature or in some chemical reactions, what happens is that sometimes A can either undergo parallel reactions like this, or it can happen that A forming B can form D also if it goes ahead. Maybe B is an intermediate in this parallel reaction scheme also. So here we are seeing that on the B pathway, we are seeing a series reaction, but at the same time, to form B and C, we are seeing a parallel reaction scheme. So in a complex reaction system, both parallel and series reactions can be involved. And the graph here shows that with respect to time, for the left hand side reaction scheme, as A concentration decreases, both B and C are increasing. But we can see that B is increasing much more higher than C. So from here you can conclude that the order of reaction of A forming B is much higher than that of A forming C. So B is the desired for this kinetics. So we can say that in a complex reaction system, both parallel and series reactions are needed. So correct answer is all of the above, since all these three statements are true for the multiple reaction systems. Moving on to the next question. To obtain the desired product in the case of a parallel reaction system, the concentration of the reactant is to be maintained at a low value by the following options. Using mixed flow reactor, maintaining low conversion, rate constant control, or none of the above. So, as I discussed in the statement here, in the choose the correct statement one, here you can see the statement one, where there are multiple reaction systems, there is a need for minimization of undesired product and size of the reactor to maximize the desired. So, what happens in this case is that to obtain the desired product in case of a parallel reaction system, the concentration of reactant is to be maintained at a low value. Definitely, we need a low value. So, how can you do that? Is first one is we have a mixed flow reactor. What happens in a mixed flow reactor is the moment you add the the moment you add the reactant inside, what happens is the reactant undergoes conversion. Why? Because the entire mixed flow reactor is uniformly mixed. So the moment you add the reactant inside the reactor, the concentration drops drastically. Concentration drop is very sharp. So you can see that concentration will drastically drop like this. Whereas in case of a PFR, it will drop slowly and it will be more like that throughout the length of the reactor, the concentration dropping will be quite low. Whereas in case of a mixed flow reactor, the reactant concentration is dropping very quickly. So to obtain the desired product in case of a parallel reaction system, the concentration of reactant is to be maintained at low value. So already we have been shown that the concentration of reactant is maintained at a low value. Why we are doing this is because maybe the other product which is forming is having a higher order than the desired. So if that is the case, definitely what you need to do is you have to go for the next flow reactor. Why? Because if the formation rate of S is higher than R, then we need to quickly reduce A. And quick reduction of A will occur only in the mixed flow rate because the mixing happens instantaneously the moment you add it inside, and that's why the reactant reduces. And that's why the favorable condition for forming of S will be reduced, and we will be getting somewhat uh, better concentration for the R. And that's why we are reducing the concentration of A and using a mixed flow reactor. Next option is maintaining the low conversion. Definitely that is not the correct answer because the desired product is R, and definitely we don't want a low conversion. We want a high conversion. So that's why we have to play with the concentration and the reactor parameters in such a way that we get high conversion for R, but at the same time we are reducing the conversion of S. Next is the rate constant control. Definitely, this won't be the correct answer because we cannot control the rate constant in any way. If R and S are two different things, the rate constants which are forming them will also be different, and there is no control about them, control in them, and none of the other. So the correct answer is using the mixed flow reactor system. So mixed flow reactor system is always used whenever the concentration is low and you need to maximize the desired product you're if you are trying to suppress the undesired. Moving on to the next question. For selectivity parameter S, S and RS, you can see is equal to R by R divided by R by S is equal to KR by KS multiplied by CA power A1 minus A2 to control the formation of desired product R, which is incorrect for A1 greater than A2. So we have been given four options and it is asking us which one is the incorrect one. So we have the desired reaction is of higher order than the undesired one. So the desired reaction is higher order than the undesired. Okay, so we know this, and we have already seen two examples in the previous questions. So from there, we can tell how this question is going to work. So how the selectivity parameter defined is uh, here you can write S and the rate of formation of R. The rate of formation of R is given by the rate constants of Kr, rate constant of Kr by Ks, effectively multiplied by the concentration terms raised to their orders, respective orders. So the respective orders you can see right here is given that the desired reaction order is much higher than the undesired. So keeping the concentration of reactant A as high as possible. If concentration of A is as high as possible, there is a good chance that S will also be formed as the time goes on. Because if we are keeping A high, what will happen is definitely it will cause formation of S also. Next we have by using the flux flow reactor. Again, in the previous question I already studied that the moment you add your reactant, it will definitely start mixing quickly. So that's why. And if the concentration of A, one second,
Yeah, please proceed. Yeah, here.
yeah, yes, yes. Okay, so for selectivity parameter to control the formation, then we have the next. So keeping the concentration of reactant A as high as possible is uh, is the favorable option, so that we can get a lot of formation of the product that is R. Next, we have by using the plug flow reactor. By using the plug flow reactor, we are definitely going to promote the formation of S. So what is that going to do? By using a plug flow reactor, we're definitely going to promote the formation of R because plug flow, uh, by the comparison of the equations, the reactor equations for the plug flow and the mixed flow, we know that plug flow reactors have better conversion rates than mixed flow for similar volumes. So by using the plug flow reactor, we are definitely going to get the desired product R. Next option is by using the mixed flow reactor. Now this option is incorrect for A1 greater than A2. As we have discussed in the previous question also, that by using mixed flow reactor, we are not only letting R form, but we are also increasing the possibility of formation of S. And because of that, it is not desirable to use a mixed flow for this reaction because already the order of our desired reaction is higher than the undesired one. So we don't need to increase the mixing and give chance for formation of S. It is better to use a plug flow reactor and keep the conversion of R higher. Keep this ratio R by R as high as possible. So that is definitely favorable, but to achieve this, we need to either use the above three parameters. So the correct answer for this one is uh, by using the mixed flow reactor. That is the incorrect option because it has been asked to it has been asked to like choose the incorrect one. So the incorrect one is by using the mixed flow reactor because it will definitely hinder the hinder the selectivity of the process. Moving on to the next question. For quantitative analysis of the series reaction systems, the maximum intermediate can be formed if fluids of different compositions and stages are not allowed to mix. Now, this is a very Get the question. So here it has been given that if you are doing a quantitative analysis of a series reaction system, the maximum intermediate can be formed if the fluids of different compositions and stages are not allowed to mix. Now, in a series reaction, what happens is that we have a reactant uh, forming the intermediate, and then we have the final product formation so going on. That will give us example A forming B and giving C. So if the flow streams of A, B, and C all are mixing together, what it's going to do is the formation of B will be hindered because because of the collision theory, as we already know, if the particles of C are going to collide with A, the interparticle collision of A itself is going to be very less to form B. So that's why it will be desirable if we don't let any of these streams mix together. Why? Because sometimes what happens is if B is forming, and maybe B will also hinder the formation of itself by colliding with the A molecules also. So it is necessary for the reactant itself to properly react so that it forms the intermediate and then the reaction proceeds further. So that's why it will be much better if we keep the fluids of different compositions and stage not to mix together. So that will be much more favorable. And that you can achieve in a plug flow reactor. That will be best to achieve in a plug flow reactor because as A goes forward, it will form B. And since the flow rate is going in the right in front, there won't be any back mixing if we are taking an ideal plug flow reactor and if the flow rates are quite high. And then the formation of C will also take place and we will have the product outlet C. So to maximize the intermediate formation, we definitely need to not let the compositions and stages to be mixed. So this statement is good. Moving on to the next one. For selectivity parameter, SRS is equal to a rate of R by rate of S. Again, similar expression. To control the formation of desired product R, which is the correct for A1 is equal to A2, i.e. undesired reaction order is equal to the desired. So here you can see that the order of reaction in K1 and K2 formation is same. So here this is definitely going to be a competing reaction. So what is going to happen here is that since both of them are going to react and compete and they both have the similar order, so the curve at which they will be the curve of the disappearance of A with respect to R and S will be same and it will follow the similar kind of pattern in the graph also. So if this is the formation, this is the decline of A for formation of R, the similar decline will happen for S also. So this kind of curve will be followed by R and S also. So what can be done in this case is that first one is the product distribution becomes independent of the reactant concentration. This is true because since both of the orders are same, no matter how much A you're going to put inside the reactor or remove from the reactor, because it will just either promote the reaction of both of them or reduce the reaction of both of them since both orders are equal. The next is unaffected by the use of a type of reactor. Again, that statement is true too because you either put it in PFR or in the CSTR, the conversion of both of them will take place at the similar rate since the order of the reaction is very important and since they both are equal. And then we have the option both A and B, and the last one is neither A nor B. So we can clearly see that options A and B are the correct answer. So both A and B, that is option C, is the correct answer for this question. Moving on to the next question. Again, similar question type. For selectivity parameter, as far as R rate of R by rate of S, to control the formation of desired product R, which correct option should be used for A1 less than A2? Undesired reaction order is lower than the desired. So, sorry, undesired reaction order is higher than the desired. There is a typo here, I would say. So, A2 is higher than A1. So, we can see that S is going to form in a much higher quantity than the R. So we have to find out which is the correct option amongst all of them. So we have been given four possibilities. So first is keep the concentration of reactant A as high as possible. Definitely not that is not favorable because if we are going to keep A as high as possible, it will only promote the formation of S because the order is higher. Next is by using the plug flow reactor. Again, that is not the correct way to go for it because if we are going to use a plug flow reactor, it will only promote the higher conversion to S, as we have discussed in the previous sessions also. Third is by using the mixed flow reactor. Now, in this case, mixed flow reactor will be helpful for us. How? Because when you add A inside the mixed flow reactor, instantaneously reactant A will start reacting and it will simultaneously produce R and S. No matter if the reactivity for the S is higher than R, but formation of R will also take place and that will promote formation of R also. So that's why by using mixed flow reactor in this situation where the order of the desired product is lesser than the order of the undesired product, it is really beneficial for us to use the mixed flow reactor. And keeping this ratio R by R as high as possible is again can only be achieved using the mixed flow reactor. So that's why we have to use the mixed flow reactor. Again, this is how the multiple reaction systems are like equated, and this is how the reactors are chosen for the selectivity parameters according to the order of the reaction and the quantity of the reactant present. So with that, Rishabh, you have to solve these questions. So that was for today's class, the questions we have seen. And if you have any doubts, you can ask.
Just to can you now we are seeing with respect to the selective parameter different combination
Yeah.
like they starting with the same a going one to desired another one to undesired and
Yes.
we are having an option like which one like generally we are telling that which one will favor the desired option like
Hmm. Yeah.
this is and a1 a2 is the with respect to the respective uh, concentration like A goes to R and A goes to S.
Yes. Correct.
So just can you just explain this? And probably we have seen like multiple options. One is A1 equal to A2,
Hmm.
A1 less than A2,
Even.
A1 greater than A2.
Okay.
Like one is like when we say A1, it is like the order of the desired reaction, and A2 is the order of the undesired
Undesired.
reaction.
Yes. Correct.
What way we can keep a general like any general scenario is that where we can keep clear idea so that we can
Hmm.
answer all these questions.
Okay.
Either they are asking which is correct, which is not incorrect.
Hmm.
So if general idea is given, then it will be useful for us from that to answer all the questions.
Yes. Yes. Okay. So the first thing you have to do is, first thing you have to do is that we have to see that if the order of the reaction is given for any competing reactions present. Whenever you see multiple reactions occurring, you have to see if they are competing together, and we have to see which order is present. So if always also another thing is whenever the desired reactions concentrate, desired reactions order is higher than the undesired one, we don't have to worry. We can straight away use the left flow reactor and we can keep the concentration of the reactant A as high as possible. So that is the first one. Always keep the reactant high whenever the desired product is on the upper hand side. Next is if the undesired is on the upper hand side, we have to keep the reactant as low as possible. On top of that, you have to use mixed flow because mixed flow initiates the mixing as soon as the reactant is added. So the chance of getting the product will increase definitely. So that's why whenever A1 is greater than A2,
Pardon, the chance of getting the product yield is less when we go for
higher.
mixed.
No,
I
no,
mixed.
it will be higher because
Okay.
what happens is that, but that is only in case of A1 less than A2. Okay,
Pardon, I am not getting that point alone clearly.
okay, okay. Uh, okay, okay. I'll just summarize it in a way. that we will see the reaction cases and then I will summarize that. Okay. Okay. So in this slide, you can see that A1 is greater than A2. It
So
means
that
that
is desired reaction is order of desired reaction is greater than undesired.
yes, correct. So in
Yeah.
that case, you keep the concentration of A high and use a
Mm.
plug flow reactor.
Plug flow
Okay.
reactor. That is clear. Very clear.
Yeah, that is clear. Okay.
Yeah.
Next is when A1 is equal to when A1 is equal to A2, we can't do anything about the reactions. We it will be unaffected by the reactor also and the product. It does not matter if you use high reactor or low reactor. Correct?
Oh, so it is independent of both the concentration of the reactant as well as the type of reactor used. Clear.
Yes, yes,
Yes.
it's
Okay.
independent.
Okay. Yeah.
Then next is if A1 is less than A2. Okay,
That is desired reaction is order of desired reaction is lesser than the undesired one.
undesired one. Yes. So
So
in
here
that
I
case,
think here it is ulta. Like maybe that
hmm,
okay.
yeah, correct.
So order of
Here,
undesired reaction should be higher than desired one. That is the point I think you have scored out that lower.
yeah, yeah, exactly. So the
Okay.
moment you see that the undesired one is higher, you go for the
Ah,
mixed flow reactor. Okay.
okay. Okay.
Okay. Yeah.
So undesired reaction is higher means mixed flow reactor will help to curtail that undesired product. Is it right?
No, no, it won't help us to contain the undesired product. It will help us
Ah,
to generate the desired product also. Why? Because
oh,
in PFR,
uh-huh.
PFR is always having higher conversion. That is by the like you can see the equation of the PFR itself. From
Correct,
there,
correct.
yeah.
Mm,
So the conversion is higher in PFR. So that's why PFR will always favor that reaction whose order is higher. So here, if I'm
mm.
using PFR in this case, the only output I'll be getting is the undesired product. My desired
Okay.
product will be very low. Yeah,
Oh,
that's why.
okay, okay, okay. Uh-huh.
Yeah,
So if I want to improve the desired product also, the best option is to go for mixed flow. Otherwise, unreacted, undesired product will be favored if I am going for a plug flow.
correct. Exactly. That's it.
Yeah. And one more question here. Actually, it is like maybe one statement we went incorrect. No? Like that was there was one more statement where we
Yeah, this one.
yeah,
Yeah, this one. Here it is
yeah.
saying incorrect, which is incorrect for us
Oh,
in
okay.
this one.
So here
So
actually one is greater than desired is greater than the undesired one.
undesired. Yes.
Okay. Then in that case, concentration of A as high as possible is correct. Then
Hmm.
using plug flow also is correct.
Yeah.
By
No,
using
no, no.
mixed flow rate,
No,
uh,
actually, using plug flow is wrong. Why? Because if you use plug flow, you will be promoting the formation of undesired also. Oh, sorry,
is
sorry.
it
No,
like
no, 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 no. I said it wrong. Actually, I'm sorry. Yeah, using plug flow is correct. You said it. Yeah,
so then only the only option incorrect option is the mixed flow. We should
makes
not
sense.
use
Yeah,
flow.
makes sense.
Okay,
Yeah, yeah, that's it.
okay, okay, okay.
Okay.
Thank you. Now it is very clear. Thank you.
Yeah, that's it. So this will be helpful for you in solving any question where you can see the selectivity parameter comes into picture, so you can do that. Okay.
Thank you.
So
Thank you.
yeah. So if you have any other doubts, you can ask for like today's classes. So,
Yeah, thank you very much because I just joined back quickly because I don't want to miss this. That's why. Anyway, thanks
okay.
for the
Okay.
information. Yeah,
Yeah.
thank you very much.
Yeah.
Shall I take leave? If
Yeah, you can take leave. I just wanted to ask that how much has Sir taught, like on what
no,
lecture
no,
you
no,
are
almost the same line whatever we have discussed.
Hmm.
It was there. Probably now the next week videos I am yet to go through.
Okay.
So probably next week, I think it is already live because of some preoccupation I could not go through today. Only I went to through these lectures also because yesterday, 2 days I was on outstation trip,
Okay.
so
Okay.
go through this.
Hmm.
Probably we are in the going in that similar direction.
Yes. Yes. Okay then. So make sure that you submit your assignments on time, so it will be
Sure, sure,
better
sure.
for you too.
Right, right.
So you
Sure,
will be
done.
giving the exam also, right?
Yes, yes, yes. Already registered.
Okay. 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 Okay
I have
then.
also registered, sir.
Yeah. Yeah. Okay. Very good. Very good. Perfect. Very good. So you have registered, then it will be better if you prepare well and give the exam. Okay, good job.
Yes, sir.
Okay, then. Okay, then I
Thank you.
think today's yeah,
Yeah.
then today's class is over. I guess.
Thank you so much. Thank you very much. Thank
Yeah,
you.
okay. Yeah, bye.
Sir,
Ah,
can I ask just one question? Actually, I was actually going through. Actually, I was also out of station till now. Also, I'm out of station only.
oh, okay,
So
okay.
yeah, yeah, same here. Actually, I'm
Hmm.
also doing part-time PhD from IIT Roorkee. So I
Okay,
have
you're doing
taken,
part-time.
yeah, yeah, part-time. So one of my this NPTEL course is a compulsory subject that I've taken, that I
Hmm.
have to produce the certificate, pass certificate from the NPTEL. So every lecture and every assignment, even the examination is very important for me.
Hmm. Yes,
So
yes.
in that point of view, I'm also not getting that much time to go through the videos on time. So I've
Okay,
selected as of now 3.5 videos of like week four,
okay, okay.
3.5 part of the videos.
Hmm.
So actually, while I was going through the videos, so I came across some doubt while like in the equations. So can I,
Hmm.
if you like permit, can I ask you one few questions?
Yeah, okay. You can ask me.
Sir, actually, there is a while solving the equations for varying volumetric flow rate for flow reaction in polymer.
Hello.
Hello.
Yeah, yeah.
There is a term
Hmm.
CT equals to FT by nu.
CT is equal to FT by nu. Okay.
G, G. And
Hmm.
after that, it is coming CT equals to P by ZRT.
CT is equal to P by ZRT.
So this equation,
Hmm.
how it has come from FT by nu, that one I could not understood.
Okay.
uh,
Uh,
I was relating with the gas equation, that is PP equals to ZRT,
hmm.
and from that we are getting V equals to ZRT.
Yes.
But from that I think it is not coming as per the given equation CT equals to PRT, because P by ZRT, because FT, that term is still missing in that.
Okay. So has sir explained it or it,
Sir, actually, he has written directly CT equals to FT by nu, and after that, direct equation has come CT equals to P by ZRT. I just actually could not relate how this equation has come from, like from the previous equation, like FT by nu.
okay, okay.
So this one
Hmm.
actually I was having like
So you want to know
confusion.
the derivation for that, right?
Yes, sir, might be the derivation, like how it has come. My question
Okay,
is how it has come P by ZRT.
okay, okay. Uh,
Even sir, one more part also.
huh.
Uh, while solving for half-life method for reaction,
Hmm.
so for the first order reaction,
Yes.
after putting n equals to 1,
Hmm.
t half we are getting 0.693 by k.
0.692. Yes, correct.
So if I put n equals to 1 here, so it is the entire equation is coming undefined.
Uh, in the first order reaction, half-life.
In the half-life equation, in first order reaction, putting n
Hmm.
equals to 1,
Hmm.
T half equals to 0.693 by K. So how this has come, actually that one also one of my questions that arises in my
Okay.
mind.
Yeah, I can answer that one. So what happens is
Yes,
that,
yes,
one second. I'll just
yes,
open that lecture itself. Where,
yes.
like, yeah.
T half it is giving Ca naught to the power 1 minus n
Hmm.
within bracket zero point 0.5 to the power 1 minus n minus 1 whole bracket divided by n minus 1 into k.
Okay.
This is the
Uh,
derived expression, kinetic
yeah.
expression for nth
Hmm.
order reaction at half life.
Hmm. Okay, one second. I'll just present it.
Sir, I have a question. During examination of
Hmm.
this subject, whether
Hmm.
it will be pen or paper examination or multiple type questions
It will be multiple
or
types.
multiple type questions, right?
Yeah.
Okay.
Okay, so here you can see that the zero order reaction is given as, sorry, the first order reaction is given as 0.693 by Q. Now, uh,
Yes, yes.
yeah. Okay, so you know the expression for the first order reaction? What is the expression for the first order reaction? Can you just tell me?
Expression for the first order.
Hmm. It will be
Yes. Mm,
ln Ca naught by Ca, correct? Is equal to
uh,
Kt. Is it right?
uh,
Tell me.
so actually, the equation that we have derived is T half. It is coming the general expression for
Yeah,
kinetic
I'm.
expression for nth order reaction.
Hmm.
Yeah.
Okay, anyway, just if you are going from the first principle, that is dCA by dt, we go from dCA by dt is equal to K Ca power n. Okay, that is your
Okay.
expression, correct?
Okay.
Now you put n is equal to 1. Okay, when you put n is equal to 1, you have dCA by dt is equal to Kc. Now, what you do, you bring Ca down and you separate the variables dCA and dt. You will have dCA by Ca is equal to K multiplied by dt. Now, what you need to do is integrate these two. Then, after integration, 1 by Ca is nothing but integral of 1 by Ca is your ln Ca. So, you will be left with ln Ca is equal to Kt. Again, Ca is changing from uh, Ca naught to Ca. So, it will be Ca naught by Ca. Okay, you get it?
Sir, can I see the equation you are writing?
Actually, I'm writing it on a notebook. So,
Okay,
uh,
okay.
anyway, that's how you uh, like I can say it verbally. I guess you can understand
Yeah,
still.
yeah. Or if possible, you can like after that you can send me the snap of the you are writing.
Hmm. Yeah, one second. Just one second. I'll just pull up the first order reaction. Okay. Uh, First order reaction expression itself. I'll show you. It is quite simple actually. The first order reaction, like dCA
Okay.
by dt, you have to do.
Okay.
And
Actually, the equation, like, what is the equation actually? I was searching.
hmm, okay, then. uh, Okay. So are you able to see the equation on the right hand side? Can you see it?
Yes.
You can see that, right? Is it visible
Yes, sir.
to you?
Yes, yes.
Okay, so you can see that the final expression is uh, log e is nothing but your natural logarithm. So natural logarithm of
Yeah.
a by a naught is equal to minus kt. Fine. Or you can see that natural logarithm of a naught by a is equal to kt.
Okay.
Understood?
Yes. Okay.
You can just write it down, I guess. Did you write it down?
Yes, yes.
Okay, so that is the case. Now, what you have to do is whenever you're going for half-life, you have to always remember that in this case,
80 equals to A0 by half.
exactly, exactly, AT is equal to
Mm,
A0 by
mm,
half.
mm.
It will
Yes,
become
yes,
like
yes,
that.
yes, yes.
Okay, AT is equal to
Mm.
A0 by half. At the same time, on the other side, KT, T will become T half. Okay,
T will become T half. Yes, yes.
yeah. Now, when you have half, you can cancel out the A naught term, and then it will become natural logarithm of 2. It will straight away become natural logarithm of 2. And natural logarithm of 2 is nothing but 0.693.
Okay,
Okay, so
okay. Natural
0.693.
logarithm of half is 0.69. Okay.
No, no, not half, not half. It won't be half. It will be 2 because
Oh,
see,
yes, yes, yes. So it will go like that. Oh, yes, yes.
yeah,
Actually,
yeah, yeah. It will
this
go on top.
minus KT, no, sir? Yeah, yeah.
Yeah, exactly, exactly. It will go on top and it will become natural logarithm of 2, and that will give you 693 is equal to KT. Then you will have the expression, this expression. That is 0.693 by K is equal to T. Understood?
Yes, yes.
Yeah. So that's how you derive for the first order. So always remember that whenever you are putting T half, you have to change the concentration term also. It has to be half, half of the initial one. So that's how you do. Okay.
Yes.
Yeah. That's
Mm, yes, sir.
hmm.
Sir, actually, one more was facing some problem
Hmm.
while deriving one equation.
Hmm.
Actually, while solving these step-by-step equations, so
Hmm.
uh, at some of the point,
Hmm.
I've got name of the equation is for second order irreversible reaction.
Huh.
The general expression that we have obtained is one by m minus one
1 by
ln,
m minus 1.
yeah, one by m minus one ln
ln
within bracket m minus xa
xa.
whole divided by m by 1 minus xa
Okay.
equals to k a naught t.
A naught T. Okay. So is this expression for the third order reaction or calculating?
Yeah, yeah. Actually, what I am getting
Hmm.
exactly the whatever part is in denominator, it is coming numerator
Hmm. Okay. So the
because due
denominator
to
term and the
minus
numerator term are
ln
the
it should come in the place of minus it is coming plus and in place of plus it is coming minus.
same. Hmm.
So
Okay.
actually I have checked 2 3 times where I am making mistake. So that expression I could not able to like is not coming as
I
per
think
the expression given in the lecture.
I think the mathematical manipulation which you are doing for your expression is not correct because if you are deriving it for the third order, make sure that the the integral for the cube, the CA power 3, which you are changing, it should be correct. Always remember that. That term you have to take care of it. And then KT will integrate as it is. Then you should not have any trouble in calculating this
Okay, actually, sir, it is a general expression.
one. Hmm.
So this expression, while solving, it should come like this because
Yes.
up to second last or third last step, my
Hmm.
expression is similar to the expression coming as per the whatever in the lecture it was
The
given.
lecture shows, right? Yeah, then
Yeah,
maybe
yeah.
you might have missed one of the parameters in maybe in
Because
simplifying the expression.
I have simply opened up the limits.
Hmm.
Uh,
Yeah,
it
maybe
is
yeah, just check that.
Mhm.
Just check how you applied the limits for that, and then you might be able to solve it.
I've opened up step by step,
Hmm.
but still it is coming like that.
Okay, so one more thing, your other doubt, right? I'll have to take a look at that, and I will get back to you, and I will tell you how that ft by nu is converting to p by zrt. Fine,
Okay, okay, sir.
I'll definitely tell you that in the next class. Uh, so I guess you need to check your third order reaction. Just take a look at it, and maybe the mathematical manipulation which you're doing to simplify the last term is not
Yeah,
correct, I guess. Just take a look
yeah,
at
yeah,
it.
might be. Yes, yes,
Yeah,
yes, yes.
just repeat it, and maybe you might get it correctly. Sure. Sure.
Okay, okay.
Okay, then we'll end today's class. Thank you very much for attending. See you in the next class, and we'll be discussing more about the reaction rates and reactors. Okay, thank you very much.
Thank you, sir.
Thank you very much.
Yes, sir.